Hey everybody, Joe Price here. So this is a follow-up video to my previous video that showcased this decimal input and output adder. So I wanted to take the opportunity to touch upon how this adder works exactly, but more importantly, explain giant logic gates. There are a lot of gates that are used in this particular build, but of course these giant logic gates will have functions in other builds as well. So just a quick reminder of how this decimal input adder works. Just input some numbers here, like 342. We can add that to, let's say, 67. Press enter, and a number of things are taking place now in order to do the calculation. And the calculation is done in binary, so we have to convert to binary, do the calculation, and then convert from binary back to decimal. And there we go. We've got our correct answer, 409. We'll just hit the clear function and just have a quick look around. Yeah, so directly up top is the decimal input machine, and right above that, over here, are storage units so that we can also store the numbers in binary coded decimal. So one of the 3-digit numbers, or up to 3 digits, can be stored in this unit, and the other number that we're adding can be stored here as well. Now, there's a mechanism that converts from BCD into binary, and part of that mechanism, there is a -3 function. I won't get into why we're using that and how exactly that works. It falls outside of the scope of this particular discussion, but suffice it to say, we need to use some giant logic gates here and over here as well for this -3 function to take place. There's a shifter as well, so it shifts the numbers to be stored in binary over here, and once both of the numbers are stored in binary to be added, then we have more giant logic gates. They're directly below me here. More giant logic gates that will actually perform this addition. This is a ripple carry adder, which consists of a half adder linked to a whole bunch of full adders. Once the addition has taken place, the answer is stored in binary all the way down here, and we're going to be converting this binary number into BCD again over here. So this machine basically does the exact reverse of the machine that we saw up top. And again, there's some giant logic gates down here whose function is to add 3 to certain numbers stored in BCD as the entire mechanism is taking place. And then once the answer has been converted into BCD format, then from BCD we're going to convert that into decimal. And these are some more giant logic gates that I use for that particular conversion. Alright, so what exactly are these giant logic gates, and how exactly do they function? So to explain all of that, let me shift to a tutorial world, and we'll start with a discussion of what these logic gates are exactly, and then we'll revisit exactly what I just showcased on that world. We'll explain the function of each one of those logic gates. Alright, so here's a general setup of a logic gate. Now, before I discuss the logic gate itself, there's just a couple of quick things that I want to touch upon. So I mentioned in the previous video how we can use dummy ghosts as signaling agents. There's a dummy ghost here currently, we can hit it, but we can also teleport it away, and we can teleport it into one of these modules. Now, this adjacent module is where the dummy ghost is going to be teleported to initially, and we see that it's going to be controlled by this lever, and it's connecting the 2 teleporters through green wire. Now, these modules have been designed by another official forum member by the name of Inominums, and they're designed to greatly reduce operation time. Basically, the idea is that as soon as we teleport the dummy ghost into this first module, the dummy ghost will be pushed by these Hoik teeth into one of the 2 pressure plates on the right side here. And depending on which pressure plate is hit, the dummy ghost will then be teleported either to this module up top, or teleport it to this module at the bottom. I'll just continue like that. Now, when it comes to teleporters, the entity that's being teleported, its position above the teleporter, the departing teleporter, is maintained at the incoming teleporter. So here, this dummy is strategically positioned on the left edge, just overlapping one tile with the teleporter here. So upon teleporting, that dummy will overlap with the Hoik teeth here and thus be pushed to the right. Now, this means that when pushed to the right, the dummy will then appear on the right when teleporting to the next teleporter, which is why the Hoik teeth in the next module are on the right. So they'll push the dummy to the left, and it'll just continue like that. Then this dummy will jump, let's say, to this module, and that's why the teeth are on the left, so on and so forth. The other thing to mention about these modules is that they are very fast. They operate in 1 game tick. That's the time that it takes to jump from one Hoik tooth to another. And 1 game tick, 1 game frame, that's basically 1/60th of a second, assuming that the game is operating at 60 frames per second. So pretty fast. Now, how do these 2 pressure plates operate exactly? It's actually dependent on the actuation state of this specific Hoik tooth. We see that it has an actuator on it, and it's connected to one of the inputs, and I'll explain the input in just a second. So basically, in a deactuated state, it'll cause the dummy ghost to hit this bottom pressure plate. Now, this bottom pressure plate is connected by blue wire, and it'll be teleporting the dummy ghost to this particular module. However, if this Hoik tooth is in the actuated state, well, this top Hoik tooth will lift the dummy ghost ever so slightly off the ground, causing it to miss this particular pressure plate and activate the top pressure plate instead. Now, this top pressure plate, it's connected through green wire here, and it connects to the module up top. So, simply put, the actuation state of this particular Hoik tooth controls whether or not the dummy ghost is going to go to the upper module or the lower module instead. Now, just so I don't have to keep bringing up the wires every time I'm trying to explain a particular path, I've actually color-coded everything. So the green path, the top path, is always taken when this particular Hoik tooth is actuated, and the bottom path, the red path, is always taken when this particular Hoik tooth is in the deactuated state, the way that we see it currently. So what controls the actuation state of these Hoik teeth are any number of inputs. So now let's take the opportunity to explain what is meant by giant logic gates, and just what are logic gates in general. So logic gates basically take some number of inputs. The basic logic gates, there are 2 inputs, and they make a decision as to whether or not to generate some sort of output through a particular output wire. So just as an example, an AND gate, both of the inputs would have to be in the on state for us to generate an output. If only one of the inputs is on, nothing's going to happen. And of course, if neither of the input is on, nor are on, then nothing is going to happen as well. So suffice it to say, logic gates just take inputs and generate some sort of output based on the combination of inputs. Now, in the real world, when we're using logic gates, we usually have to combine logic gates in certain ways so that we can generate multiple possible outputs. But in Terraria, we have this unique opportunity to, instead of using basic logic gates and combining them together, to just create giant logic gates, such as the one that you see on screen. Now, these giant logic gates have any number of inputs, and thus will have any number of outputs as well. More specifically, if you have n number of inputs, as you'll see in a moment, you'll always have a maximum of 2 to the power of n number of outputs. So this is really convenient because in a lot of the machinery, we actually do want to generate a lot of outputs, and you'll see why in just a second when I look at various examples. So in any event, let's first discuss this particular logic gate. And I've, just for illustration purposes, I've used 3 inputs, but of course we could extend this to as many inputs as we want. So when all of the inputs are in the off state, and the off state is just defined by 2 things. Number one is whether or not any of these torches are on. So here's the on state, here's the off state. But more importantly, the on and off states are controlled by the actuation state of the Hoik teeth in these modules. So the off state is also defined by this particular Hoik tooth being in the deactuated state, whereas the on state would be defined by this particular Hoik tooth being actuated instead. So the inputs will control ultimately which path is taken by the dummy as it's passing through all these modules. Alright, so with A, B, and C all in the off state, the dummy ghost, it'll jump to this particular module the moment we hit the lever. Then it'll proceed down the red path to this module, and then down the red path to this module as well. And then down the red path, it'll activate the 8 here. Now, the output, it's basically a piece of wire. So here it's just a green wire. And other outputs, they're blue wires instead. And this will have some downstream effect. So that 8 could correspond to further operations down the line, or it might affect the actuation state of particular Hoik teeth, or turn torches on and off. There are various possibilities here. Alright, so as it stands, if I were to pull the lever now, it'll just send the, or generate a signal at the 8 position. Just like that. Now, there's one other thing to clarify here. This is a pulse-based system. Terraria is a pulse-based system, whereas in real life, logic gates, the input signals and the output signals, they have sustained currents in them if they're in the on state. So if we, let's say, churned A into the on state, there would actually be a sustained current here. Same thing with the output, there'll be a sustained current there if the output is in the on state. Now obviously we don't have that in Terraria. When you send a signal down a length of wire, you just send a pulse. There's no sustained current there. Which means that the way that this is set up right now, it seems as if this is not a logic gate at all, but just a simple toggle. Because if I pull the switch again, well, all of a sudden I'll send another pulse and it'll churn something off. Just pull it again and turn it back on. However, in these electronic systems, we can simulate logic gates by having local or global resets, meaning there's some other part of the mechanism that will shut this off before this logic gate is activated again. This way, it'll ensure that every time we pull the lever and all 3 inputs are in the off state, then we'll always be generating an on state with our output. But we don't have to concern ourselves with this that much, because we're not here to discuss reset systems. We're just here to discuss how to generate an output given some combination of inputs. Alright, so let's take a look at some other possibilities. So let's say that A and B are in the on state and C is in the off state. So based on the design of this gate, since A is in the on state, when the dummy ghost arrives at this module, it'll take the top path to this module. Then because B is in the on state, it'll take the top path to this module. And since C is in the off state, it'll take the bottom path, the red path, and it'll activate the signal at position 2. Note that for B and C inputs, they affect all of the modules that are vertically oriented in relation to that input switch. If we just pull up the wire here, note that the red wire here, it connects to the Hoik tooth at this position in this module, and it also connects to that Hoik tooth at that position in the top module as well. Okay, that's why you have this blue line that passes through both the modules, and just like this blue line passes through all 4 of those modules. Alright, so in any event, we said that our predicted path here would result in churning the light on at position 2, and that's exactly what happens. All right, so just one more example here. So let's say that A and C were on, and now the path that we would predict would be as follows. So again, we would start at this module. Because A is on, we'll take the top path to this module. Because B is off, we'll take the bottom path to this module. And since C is on, we'll take the top path and send an output signal at position 3. Yeah, just like that. Incidentally, when the dummy ghost reaches the very end, so any one of these 4 modules, there's a red wire here that actually connects all of these teleporters and hits all the pressure plates. This just ensures that the dummy ghost will return back to the starting position here. And note that there's some Hoik teeth on the side, which will just push the dummy ghost so that it's in the proper orientation before being used again. This isn't always going to be the setup. Sometimes the dummy ghost will proceed further on instead of being teleported back to the starting position. It just depends on what the build is. It depends on what these outputs are exactly. But again, that's beyond the scope of our discussion here in this particular tutorial. Okay, so this is how these giant logic gates operate. But of course, let's take a look at some examples so it makes a little bit more sense how these can be utilized specifically. So the first application we're going to take a look at are half adders and full adders. Now, to understand what is meant by a half adder and what is meant by a full adder, just have to briefly talk about how binary addition takes place. And a good way of thinking about it is by thinking about how you would do addition using decimal numbers. For instance, if we added 4 and 5, well, the output would be 9. And nothing would carry over to the tens position. But if we added, let's say, a 4 and a 7, well, the outcome would be 1, and then we would carry a 1 over to the tens position. Well, it's the same thing when it comes to binary numbers, but it's a lot simpler, because with binary numbers, at each position, you can only have 0 or 1. So what a half adder does, it simply adds 1-bit binary numbers. So it performs the addition of either 0 plus 0, 0 plus 1, or 1 plus 0, and also 1 plus 1. So the outcome of 0 plus 0 is just 0. The outcome of 0 plus 1 is 1. And the outcome of 1 plus 1, well, it's 0, and you carry the 1 to the next bit. So that's what we're trying to achieve here, this kind of addition. So right now, both of these are 0, and if we were to add these two together, the outcome would be 0, and we would carry over a 0 as well. So based on the setup of this logic gate, well, since this is in the off state, the dummy ghost, when it starts at this particular module, it'll take the bottom path to this particular module, and because this is also in the off state, it'll continue taking the bottom path. This will light up, so that will correspond to 0 as our output, and in purple, that's the carry, so that's 0 as well. However, if, let's say we were adding 1 plus 0, now all of a sudden, we'll start this module, we'll take the top path instead to this module, and we'll take the bottom path, and we'll end up with an answer of 1 with a carry of 0. It's the exact same thing if this was turned on and this was off, so this is now 0 plus 1. And yeah, we would start this module, take the bottom path to this module, and then take the top path and end up at the same position. Just to demonstrate that, yeah, just like that. Finally, if we wanted to add the two ones together, well, the outcome would be, again, 0 with a carry of a 1. So at the first module, we'll take the top path. At the next module, we'll continue taking the top path. Yeah, just like that. So this is just a very basic half adder. So let's compare that to a full adder. So a full adder also adds the two binary numbers, just like the half adder. The difference is that it involves the carry as well. Okay, so again, in decimal equivalence, it would be like something carrying over to the tens position. and then we obviously have to involve the carry in that addition. All right, so let's see how this would work. If the carry was 0 and both of these were 0, then adding all three zeros together will just give us 0 with a carry of 0 to the next bit. So this is what we would end up with, just 0 and 0. However, if any one of these were turned on, that would essentially mean 0 plus 1 plus 0, which means the outcome is 1 with a carry of 0. So right there, a 1 with a carry of 0. If any two of these were turned on, that would be the same as saying 1 plus 1 plus 0. So then the outcome would be 0 with a carry of 1. Right up here, 0 with a carry of 1. And if all three of these were turned on, well, 1 plus 1 is 0, plus a further 1 is 1. And because 1 plus 1 gives us a carry of a 1, altogether we will end up with 1 and then carry the 1. Again, this is exactly the way you add numbers in decimal as well. But like I said, in binary it's a lot easier. All right, so if we take a look at the setup here, well, again, if all of these are turned off, starting from this module, it's always the bottom path that's taken, so we'll jump to this module, and then jump to this module, and then we'll end up activating this particular output. Yeah, just like that. If, however, let's say these two are on and this is off, so again, 1 plus 1 plus 0 would give us 0 with a carry of a 1. There we go, 0 with a carry of a 1. And we saw the path here from the particle trails. We took the bottom path from this module to this module, then we took the top path, and then took the top path as well to activate at this position. So if we want to create an adder that is capable of adding numbers of any size, then we start with the half adder, and then we connect it to a whole bunch of full adders. So here's a practical example of it. So here we can do addition of numbers between 0 and 7. So we'll input the first number over here between 0 and 7. We'll input the next number here between 0 and 7. The 1, 2, and 4 just indicates the weights of the bits here. So if I turn on this one and this one, well, that's a 3 in binary. If I turn on this and this, that would be 6 in binary. So the way the addition is going to take place here is it'll add this to this. So this will be 0 plus 1. So the output will be 1 with no carry. So at the next position, we'll add 1 plus 1. And again, the carry was 0. So 1 plus 1 will give us 0 with a carry of a 1. When we carry the 1 over, well, at the next position, we'll add the 4 plus, at the next bit, we'll add the 1 plus the 0 with a carry of 1. So 1 plus 1 plus 0 would give us 0, and we'll carry 1 to the next position. Now, the next position would have a weight of 8, so in the end, we will end up with a 1 at this position and a 1 at this position, so our answer will be 9. Yeah, just like that. And in terms of these giant logic gates, so we started with the half adder here, and bring up the wiring, but it'll be a little bit complicated to explain, but suffice it to say, this is just a compressed version of the half adder that we've demonstrated already. So after going through the half adder, to take care of the addition between these two numbers, the 1 here, the 0 here and the 1 there, then it jumped to the full adder, and it considered the carryover. So at the next adder, the full adder, we added the 1 and the 1 here. We had a carry of 0, so this full adder took care of that. And again, the full adder here is just a compressed version of the full adder that we've just looked at moments ago. And the final full adder takes care of the carryover from the previous full adder and takes care of the addition of this 1 plus this 0 plus that carry. Yeah, so that's basically how it works. Do note that I'm going to be offering this particular tutorial world for download, and I'll be providing some schematics as well, with wires and without. So you can take the opportunity to study the wiring here and verify that it indeed works exactly as illustrated over here. All right, let's take a look at more examples. So next up, let's come over here. Next up is the binary to BCD converters. And the BCD to binary converters work in similar fashion. Now, these converters, they actually involve two repeating mechanisms. So there's a shifter, which is not shown here, which I won't be going into too much detail for the moment. And there's also a +3 function. The +3 function, it basically examines what is currently being stored in BCD format. And then if it turns out that numbers 5 through 9 are being stored, it converts them by adding 3. So if we had, let's say, 5 stored, well, it'll take that 5 and, well, shut these off and convert that into an 8. Anything below a 5 does not get converted. There'll be no change. And based on how the shifter works, nothing above a 9 could ever appear here. So we only need to concern ourselves with numbers from 0 to 9 appearing in BCD. Okay, more importantly though, how does this logic gate work exactly? So this is lacking the kind of symmetry that we saw in the previous examples, and let's see why. So the first module is now controlled by the on or off state here of our most significant bit. Now when this is in the on state, well, that means the dummy signaling agent will now proceed through the top path to this particular module, and that's controlled by whether or not the least significant bit is in the on or off state. If it's in the off state, well, it'll take the bottom path, which means that we'll be converting the 8 to an 11. And indeed, we have 8 stored in BCD below. If, however, this 1 is in the on state, well, that means the dummy ghost, after moving to this module up top, they'll take a further top path and then convert 9 to a 12. And indeed, it converts a 9 because we have 9 stored in BCD here. However, if that 8 is off, well, if the 4 is on instead, then the dummy ghost will take a path through here, take the bottom path to this module, and now since 4 is in the on state, well, we'll take the top path to this particular module. Now if 2 is off and 1 is off, then we'll just take the bottom path and take the bottom path as well, and yeah, there'll be no change, because as we just said, if it's 4 or less, that'll have no effect. But if, let's say, 2 is in the on state, well, from this module, we'll take the top path to this module, and if 1 is off, well, we'll take the top path here, and then we'll take the bottom path here because 1 is off, and then we'll be converting the 6 to a 9. Again, we have 6 stored in BCD here. Yeah, so that's basically how this functions. And if you're wondering, how are we supposed to do these conversions? Well, simply put, these particular wires that pass through these torches and are attached to these levers, they can snake around here, and they can pass through Hoiktronics, and these Hoiktronics can be used to actually convert these numbers by adding 3 to them. I'll demonstrate that in a second, but first things first, let's verify some of the things I mentioned. So let's say only 8 is on, and yeah, we see that we saw from the particle trail how the dummy ghost started here, jumped up here, and triggered this particular output. If we have, let's say, 7 input, so our predicted path would be from this module, take the bottom path since 8 is off, take the top path since 4 is on, take the top path since 2 is on, and take the top path since 1 is on as well. So we'll end up converting that 7 to a 10. Yeah, just like that. Alright, so over on the far right, this is what it looks like. It looks like when it's fully compressed. We saw here that we had 1, 2, 3, 4, 5, 6 modules in this giant logic gate. Likewise here we have 1, 2, 3, 4, 5, 6. And we have these short tracks that will do the conversion from one number to the other, meaning we'll add 3 to those numbers. So for instance, if I had an 8, well, it'll be converted to an 11. If I had a 6, it'll be converted to a 9. But if I have anything less than 5, so let's say a 3, nothing will happen. Alright, so one more example of a giant logic gate, and that is the converter from BCD to decimal. So basically we have 4 inputs yet again, and this time we have 10 outputs corresponding to the digits 0 through 9. So for instance, let's say that we had 6 stored in BCD here. And if we predict the path, so starting at this module, since 8 is in the off state, we'll take the bottom path. Since at the next module 4 is in the on state, we'll take the top path. At this module, since 2 is in the on position, we'll take the top path. And since 1 is in the off position, we'll take this bottom path. Yeah, so that corresponds to a 6, and indeed, we're storing 6 in BCD, and we'll end up with 6 in decimal. Yeah, just like that. Let's do another example. Let's say we had 9 this time. So, starting at this module, since 8 is on, we'll take the top path. Then at this module, since 1 is on, we'll take the top path as well. We'll end up with the 9. Yeah, exactly like that. Alright, now, when it comes to converting into decimal, it'll be a good idea to have some nice way of displaying it. So I use a 7-segment display up here, and the 7-segment display, it's connected to all of these different tracks. So depending on which track the signal agent goes down, well, it'll hit some of the pressure plates, which will activate some of the segments in the display. So let's take a look. So let's say we had 6 here. Turn this on. We saw there from the particle trail it went down this track. And yeah, it turned on 6 out of the 7 segments to create the number 6 there. Shut that off. And let's do another example. So let's say we had something like 3. Yeah, there we go. 3 popped up. And again, we saw from the particle trail that the dummy ghost went down one of these tracks. Alright, so lots of examples of these logic gates, and this is the unique opportunity that Hoiktronics brings to the table as far as creating logic gates are concerned. This is why we don't actually have to bother with creating AND or XOR logic gates or any of the other basic logic gates, because we have this opportunity to generate these giant logic gates with lots of outputs. So we can actually accomplish quite a number of things just from one mechanism.